Hello again, welcome back. Hope everyone's quarantine is treating them well and that everyone is staying safe. For those of you who have sent me things that I have not yet graded, I do apologize for that. Apparently, even with the quarantine, my organization is not the greatest. I do apologize for that. Appreciate everyone's flexibility. And you guys being flexible with me so I can be flexible with you. Some of you all have, still have outstanding assignments. So, just get those in and need everything in by the 10th of May, if not sooner, preferably sooner, but absolutely have to have it by the 10th of May. Now, just very quickly here, a quick overview of what we're going to work on. And here, we need to talk about evolution today. And for whatever reason, it's been kind of a controversial subject, but just please understand there is zero controversy within the scientific community as to whether or not evolution occurs. There's some question as to how it occurs exactly. And we're going to talk about that here in the next little bit. So let's look on page 190. Okay. And you'll see there the Barringer Crater, Nose Meteor Crater National Park in Arizona. And that is an impact crater from, relatively recently, just about 50,000 years ago, which is, it sounds like a lot of time, and it is a lot of time, but geologically speaking, it is not that great of a time period, okay? And it's a very fresh crater. You can see that because it still looks like a very obvious impact crater, okay? Older craters, guys, those are not going to look very new or very crater-like, to be honest, okay? And this is just one of many, many times that the Earth has been hit by a giant meteorite. Okay, and on average, about every few million years or so, the Earth is going to get hit. Okay, and not to scare anybody, but we are actually overdue for another serious impact. Okay, we've had some close calls. Okay, on average, about once every 2 months or so, you will see an article in the news that they recently discovered your meteoroid may be on impact or on course to impact us. And, there'll be a small mention in the paper there, and then, they'll do further observations, and they'll say, hey, well, actually, okay, with more data here, we've been able to get a better calculation in here, and it's not going to hit us. And you see this here. Honestly, guys, though, it is not the meteoroid or the asteroid or whatever that we know about that we're going to need to worry about. Okay? The ones you're going to need to worry about are the ones that we don't see. Okay? And you're looking at things like in 1988. 1988, right there, we had a undetected meteoroid pass through the area of space where the Earth had been 4 hours previously. Completely undetected. If it had come along 4 hours sooner, we would not be here having this conversation. And okay, we all know about the meteoroid impact that killed the dinosaurs. The ones that weren't killed by the impact, which would be most of them, were killed instead by the massive cooling of the planet. And that is what led to the dinosaurs' extinction, rise of mammals. Okay? And it's an event that kicked off a large amount of evolutionary activity in a very short period of time. So we're going to look here. Chapter 11 is going to discuss the evidence and the history behind evolution. And in Chapter 12, we're going to talk a little bit more about the nuts and bolts of the process. Okay? Yeah. People, they will get bent out of shape, okay, over the theory of evolution. Scare quotes. Okay, and these are people they will use the fact that it is the theory. Okay, they'll use that in the popular sense of the word theory. Okay, just like I've got a theory that the lizard men came and are running everything. That's not a theory, at least in scientific terms. Okay, think back to the very first lesson, guys. A theory, when we talk about science, that is the best explanation we have that meets all available evidence. Okay, so the best explanation we have for what we're seeing here is, in fact, evolution. And evolution by natural selection. We'll talk about what that means here in just a second. So, and when you hear about it, it's really simple. There, it's not some world destroying thing. There, it's fine what some elements make it out to be. Okay. Now, if you look there on page 191, you've got the ostrich, you've got the ray, you've got the emu. 3 flightless birds, separated by oceans and entire continents and everything, but you can see they all look very similar, right? They've all got very similar characteristics. Okay? And that is one of the clues that we have there that kind of tells us, hey, maybe some animals evolved from other animals. Or maybe they evolved all from a common ancestor. Maybe these all 3 had some sort of common ancestor. Okay? And, see that word boldface there on 191, biogeography. That is just saying in there that, living things are adapted to the geography of the area that they live in. Okay? It's not rocket surgery. Of course they're going to be adapted for it. Okay? You're not going to have something like an ostrich hanging around 10,000 feet below sea level. They are adapted to where they are. Okay? They've all got a common ancestor. Yeah, if you look on 192, okay, you see that word up there, comparative morphology. What they're doing is they're just comparing how these different animals, those organisms look. They're comparing the similarities, they're comparing their differences there, they're just comparing. They see they're all very similar because they have very similar roles in their environment. Their environments are all pretty similar, so they're all going to be, pretty closely adapted to those environments. They're going to look pretty similar. Okay? And, the thing is their mindset that was prevalent up until about the 1840s to 1860s was that all species were exactly the same. They had always been the same since the dawn of time, which Bishop Ussher calculated as being in the year 4004 BC, October 23rd, 6 o'clock in the morning. How he came up with that exact time is look that up if you want. I don't really know. But basically, the idea was that everything can stay the same. It was always the same. Okay? And they started testing this, and little by little, guys, they found that these things just didn't work. For one thing, fossils. Okay, fossils, of course, is some preserved sign of evidence of some biological activity, either a preserved organism, like a dinosaur bone or a trilobite or whatever, something stuck in amber, sign that something had been alive but is no more, like for example, scat, preserved poop, etc., things like that. Okay, but these things they lasted for a while. The idea was that, but okay, comparative morphology. Why are these things so perfectly adapted to their environments when they're so far apart? Okay, why are we seeing things that existed but don't anymore? Why are we starting to see some intermediate forms? Okay, why are we seeing birds with teeth like the Archaeopteryx? Okay, why are we seeing these things? And then, okay, you also see things with geology. Okay, this is where we start to get to the age of the Earth. Okay, people were saying, like we said, the Earth was roughly 6,000 years old. Well, Lord Kelvin, you guys have probably heard of him. He was a scientist for a number of things here. Or one of the temperature scales is named after him for things. But Lord Kelvin, once they had done the work and they had figured out that the Earth's core was a big ball, big sphere made of solid iron and nickel with a liquid center, but the outer core was solid. Okay, what they did, Lord Kelvin got to thinking, okay, is the Earth really that old? Because if we got this big iron nickel ball, is it really going to cool that fast? So what he did was he made a series of spheres, of molten metal spheres. What he did was he made these spheres of all different sizes of iron and nickel. And what he would do is he would have these forged, and he would time how long it took for them to cool. Okay, scientific method in action there. Their good old experimentation, and is just basic mathematics. He figured, okay, the Earth has got to be at least 10,000 years old. Okay, if not longer. Okay, it has to be at least 10,000 years. So right there, that's almost twice as old as we thought it was. Okay, and then we looked at other things. We looked at how long. Excuse me. We looked at how long it took for sediment deposition. They would actually come and they would measure how thick the sediment was in a given area. They would come and they would measure it. They'd come back in a year. They would measure it again. And you had this minute, like barely visible, there, or barely perceptible changes in thickness, but they wouldn't have that. And so they could calculate, okay, piles up this much per year in very, very gradual increments. And they would know, oh, okay, based on how thick these strata of rock are, deposition rates, that, okay, the Earth has got to be much longer, much older. Okay, and bear in mind, and guys, this is before they even had radioisotopes. Okay, they didn't even have the nuclear or isotope possibility that we have today. But they were able to calculate this just by what they could measure. And between that and some other things, like they actually measured the erosion rate at Niagara Falls. They would say, okay, the brink is here this year. Come back in a year, it's over here, very gradually. They were able to figure all this out. And so they realized that, hey, the Earth is actually not 6,000 years old. It's actually several billion years old. And we're to the point now, radioisotope, their erosion rates, everything. We've all kind of figured this out. The Earth is roughly 4.6 billion years old. That's 4,600 million years. Okay, that's a long time. And so let's look on 192 there. Flurry of new ideas. Okay. Okay. People are going to want to do this. They're going to get new evidence that doesn't seem to fit. Well, old theory has worked so far. So let's see if we can fit this in. They're going to say, okay, maybe the species have always been here. Maybe they've always been intact just like they have, but, maybe the Earth's a little older. Okay, we can work with that. Seemed okay. And though that still didn't explain, the intermediate fossils. Okay, it still didn't explain how if you had a complete enough set of fossils here, you could actually watch this organism turn into this organism. Okay, so Frenchman, and there you see his picture. They're there on 193. Okay, Jean Lamarck. He came up with the idea that, okay, organisms, they can inherit acquired characteristics. In other words, it's here, okay, like the giraffe. The giraffe would say that, okay, he stretches his neck up to get at the higher leaves, the higher acacia leaves. Excuse me. And, okay, his neck gets a little bit out of shape, but okay, that's going to stay. So that giraffe's offspring are going to be the next generation. Their neck's going to be longer. It's going to keep going, and little by little, they're going to pile up, which actually kind of laid the groundwork for Darwin. We're going to get there in a minute. Okay. He also believed things like if you cut off, and bear in mind this is the 1800s. They didn't have compunctions about doing stuff like this. There, if you cut off a mouse's tail, next generation's tail is going to be shorter or non-existent. Well, many generations of mice had to have their tails cut off to disprove this, but they did disprove it. Okay. So now this brings us up to the gentleman you see in the corner of 193. Charles Wallace. Frat boy. Slacker. Kind of a jackass, honestly. Why, if it's over here, or pointing at me there, so whatever. But the Charles Darwin, rich frat boy, okay, rich family to begin with, up there because his grandfather was Erasmus Darwin, noted philosopher, or very rich man, made a lot of money that way, and of course he married money. He married Emma Wedgwood, who was his cousin. Okay, ironically enough, the guy in charge of evolution and natural selection. And there he actually married his first cousin. And Emma Wedgwood, heir to the Wedgwood furniture. Okay, some of you guys might be like the same pottery, but rich people marrying other rich people. And so he went off to school, basically because that was what you did there. The rich people there, they had to go to school or they had to get an education whether they wanted it or not. That was just how things were done in the 1800s. Okay, and Chuck here, he actually shares a birthday with Abraham Lincoln, February 12th, 1809. Okay, so some people celebrate Lincoln's birthday, some people celebrate Darwin Day. But Chuck here, idle rich. By his own account, he didn't really care anything about his studies. He didn't really care about college. He would be a dude bro today. Basically, he just wanted to go out and shoot and hunt, hang out with his guys, drink, etc., etc. And flunked out of college. Family tried to get him on as a seminarian. Didn't take. He ended up going on, had an interest in the natural sciences, what we would now call biology. He had an interest in animals and plants and that sort of thing. Okay? So he's there. Basically, the family wants him out of their hair. So, age 22, here, or so, 18, in 1831, he boards, it's the HMS Beagle, okay, which is a ship of the Royal Navy. There, they are on an expedition to explore the Galapagos Islands, which are off the coast of South America, off the western coast. Okay, they're exploring and mapping just to see what they could see. Darwin signs on as the ship's naturalist, and also as what was called the captain's gentleman. The idea being at the time that the captain being of noble blood and being an officer could consort or fraternize with those enlisted under him, as they were both beneath his station and under his rank. So to keep the captain company, they brought a young gentleman of leisure on board. That gentleman was Charles Darwin. Okay? And they set sail. They're gone for 5 years. And they're traveling they're mapped in the Galapagos. And it's here that Chuck starts to see some things that really he kind of questions in his beliefs. Okay, Chuck took 2 books on board with him. He took a copy of the Bible. He took a copy of his friend Charles Lyell. Those were both the Principles of Geology. Okay, the Principles of Geology was laying out that the Earth actually was several billion years old. Okay, instead of just a few thousand years old, it was several billion years old. So it's basically a million times older than previously thought. Okay. And what Charles sees there is he sees a number of things. First off, he sees a number of organisms there. He sees a number of things that, of course, no one's ever seen before. And he's seeing things that are now prime examples of what we call island biogeography. Okay, organisms that are on islands, they are going to tend to be bigger. Okay, they're not going to, in most cases, have any real fear of humans or other large animals because a lot of times the things that eat those things aren't going to be there. So if you have no reason to evolve of a fear of large things there, or when a large thing comes along, you're not going to be afraid of it. Okay, he wrote that, again, product of his times there, that he didn't need a gun because and to do any hunting if he was so inclined, because he was actually able. The bird would be perched up in a tree, and he was actually able to just take his rifle and just knock it off. Physically just push it off the tree branch there. They hadn't evolved. Okay? And he's seeing a number of strange organisms that were adapted in place, but what really caught his attention were the finches. Now, a finch, okay, it's a little bird about the size of a robin, give or take, just a little bird. And the thing was, though, that every island he went to, okay, the plants were all just a little bit different. And what he saw was that the finches on this island over here, their beaks were perfectly adapted to enable them to get whatever plant matter was on this island over here. The ones over here, their beaks were maybe a little bit heavier, a little bit stronger, thicker maybe, and more powerful, because the nuts or the plant life over here that was easier to get to. Maybe this one here, the shell was harder to crack, so they needed a stronger beak. This one over here, maybe in order to get to the seeds that were deeper down in the flowers, they had a longer bill, okay, and so on. Okay, and so what he noticed was, okay, they were all adapted to the circumstances, okay, and he saw that those that weren't adapted to that island didn't get on as well. Okay, so he went. He made his notes. He made his drawings. Collected specimens to bring back to England. And he goes. And he looks at this, and the more he sees of it, the more he realizes that, hey, wait a minute. Okay, they've had billions of years. Okay, and circumstances can change from one island to the next. Who's to say that they haven't changed previously? Okay? And what he sees is that okay, eventually he realizes that okay, these species have had some kind of change. They have had to change over time, okay, in order to best meet the situation that's there. Okay? And so what he finally realizes, okay, it's not so much that they changed over time. Okay? He realizes that pretty early on, but why this happened is why he's famous. Okay, he comes up with the principle of natural selection. Okay, and that is sometimes referred to. You'll hear it referred to as survival of the fittest sometimes, and that's kind of an oversimplification. But basically, what happens there is that nature chooses the characteristics that are going to be advantageous. Okay, and organisms that meet those criteria, those are going to be the ones that are going to survive. They're going to reproduce. Okay, and again, this was nothing really new in one sense. Okay, people have been artificially selecting traits that they find desirable for since before there was history. Okay, we talked before. You take a tomato. Or, well, I don't like tomatoes. Okay. You take an apple. Okay, we like apples. We like tomatoes, French tomato, whatever. You take an apple, and here's this apple. This nice, big, thick apple that tastes like cardboard. Okay, you take this apple over here. This apple over here, it's sweet, it's tasty, it's juicy. It's about that big. So you take your nice big cardboard tasting apple, you take pollen from this guy over here, you implant the pollen on this apple over here that tastes good, but it's tiny, and then hopefully you get an apple somewhere in the middle of there, tastes a little sweeter, a little bit bigger than the small one there, and you keep going until you get, say a Honeycrisp or whatever. It's been doing that for years. People have been selecting the traits they want, since there's been agriculture. what Darwin was saying is that instead of people selecting what traits are advantageous and what its ones are going to get to reproduce, nature's going to do it. And nature is saying, okay, this finch over here is got at the beak that can get in inside that flower, get those seeds out. Okay, this one's not. This one's going to be the one to reproduce. This one's going to be the one to survive. Okay, and that is natural selection. Basically, is that in a genetically variable population, okay, though are going to be different traits, and those with different traits are going to be that have an advantage. Those are going to be the ones that are going to be favored by by the conditions of their environment to survive. Okay, and those that don't have those conditions, they may die off, they may not die off, but eventually, guys, what's going to happen are that the ones that had the favorable conditions there are going to reproduce at a greater rate, higher rate, faster rate, more efficient, until eventually they're going to outnumber the other ones. And they may, over time, completely replace the other ones. They may not. Okay. Now, that is the theory of natural selection. Okay. And thing is here, guys, nature will start selecting for this trait. It'll select, it'll select, it'll select. Then over time, some other trait will become advantageous, and that's going to be passed on and passed on and passed on. And enough of these things are going to start to pile up that eventually things are going to be so far different, they're going to get further and further apart, that eventually they're just going to reach a point where they're no longer the same species. Okay? And we'll talk about that more in our next chapter. Okay? Now, it's pretty simple. And honestly, it is. That's the beautiful thing about all this, is it's so simple yet so, vital. And Charles Darwin, he knows that, okay, this is still some pretty heavy stuff up at the standards of the 1840s or so. He spends the next 20 years getting all his ducks in a row. He knows that, okay, I'm going to write this up, I'm going to publish this, it's going to be huge, it's going to change the way people think on science, it's going to be a huge thing. Okay, I mean, even today, he's getting static over it. He's been dead for almost 200 years. He's still getting grief over it. Okay, and he's thorough. He is ridiculously thorough. He writes a book. I had a chance, it's several years back, to read The Origin of Species. It's a book about that thick. And the man spends 20 pages talking about breeding pigeons. Okay, and I'm ashamed to say I could not make it through because, okay, it was groundbreaking in its day, but, this is also the stuff that's now taught in a 101 class, so, I didn't finish it. But, still give the Chuck all the props. And what finally prompts him to publish is his friend, Alfred Wallace, good friend of his. Okay, they're corresponding, they're writing. Okay, don't think they had typewriters then, so it was literally, "Dear Alfred." Okay, then time frame being what it is a month or two later, "Dear Charles." Okay, and so one day Chuck gets an email. He gets a letter. Okay, from his friend Alfred. It's like, "My dearest Charles, I've recently come to the conclusion and that species will change over time. And this is due in large part to natural selection." And Chuck's like, new? Goes and Alice calls up his publisher. He walks over to his publisher, sends his publisher a manuscript. And proving the maxim once again that credit goes to whoever it is that publishes first, whether or not they're the ones that actually came up to it. Chuck publishes first. That's why we have Darwin Day, and not Wallace Day, and why Alfred Wallace is now the answer to a trivia question. Okay. All right. So now we get into the evidence. Okay. We talked about the intermediate forms. We talked about how you can see the different organisms. There you can sort of see the intermediate form that was kind of progressing throughout the fossil record. Okay? You can see how different animal was existed for a while, then they just stop in the fossil record. We talked about all that. Okay. Now, you look at the fossil record. Okay. And you also look again the radiometric data. That also shows you again just how far these things can come. The process. This is where they change. Okay. You look at the intermediate forms. You can look at all that up there. You can just see the fossils. Okay. So that's one major piece of evidence. Okay. You can also see things like you see. Where is this picture? You see things. You can see the different layers. There's the Earth up there. Okay. You can see evidence of continental drift, like you see on page 200. Okay. You can see things there. You look at the map, and you can just see it there. You can see where South America and Africa. You can see how the eastern part of South America and the western part of Africa, they look like they just sort of fit in. You can see where they split apart. You can see how the fossils line up in those locations. You can see evidence of seafloor spreading at the bottom of the ocean. Okay, so you can see how the continents move. That right there says that hey, but the continents weren't always in the same place. Okay, like just for example, Kentucky. This area used to be underwater. Okay, if you can go out and see fossils of seashells in this area. Okay, so you can see right there that okay, the landscape changed. So of course, the animals and plants would change. Okay, see the geologic time scale there, 202. Okay, there we go. 204. Okay, you can see the process. It's there. The twin processes, you have morphological divergence and morphological convergence. Okay, you can see how the common ancestor, okay, the pterosaur, chicken, penguin, porpoise, bat, human, and elephant, they all had basically the same ancestor, and you can look at them, and you can all see that these are all arm bones. Okay. You can see the basic structure there. You can see how they've all diverged, okay, from that common ancestor. But you can all see that they're all related. You can all see that these are formed in terms of forelimbs here. Okay, so you can tell that they all came from common ancestry. You see over here morphological convergence on page 205. Okay, all these flying animals, they all had a common ancestor. Okay, and they all sort of evolved over the same thing. And there they all evolved of some sort of wing, albeit from different ways. So they all evolved that wing. Okay. You look at DNA evidence, which was not something that Charles Darwin had available to him. You can see there the genetic makeup of these different organisms. You can see how they all kind of change there. Starting with baker's yeast and working up, you get a lot of the same material, but they all kind of change. You can look at embryos. Okay? You can see how they all have a similar form, even if they end up or growing into something different there. Okay? These are all signs there that yes, things do evolve. They do change over time. Okay? That is chapter 11. Chapter 11? Yeah. Going to cover chapter 12 in the next video.